It's Paul Bamberg back with another Math 156 script, this one designed to investigate questions of whether a set of observations are consistent with some assumed probability distribution, and this is based on two examples from the textbook. I would suggest looking at example 3.9 and 3.10 before you proceed any further. Okay, you've done that. Let's get going. So this first example is rather artificial. You have some data that are perhaps the result of random samples drawn from an exponential distribution with parameter 1. And here are the data. I have managed to replicate the data in the table in the middle of page 65. And what this says is, reading from left to right, the number of samples that are between 0 and 0.25 is 30. The number between 0.25 and 0.75 is again 30, and so on, and so on. Now, the hypothesis is that these data come from an exponential distribution with parameter 1, and R has built in exactly the function we need for that. It's p(exp), which gives the probability that the value of an exponentially distributed random variable is less than or equal to some number. So if I take 100 times this probability for 0.25, I get the expected number of counts in the first bin. Subtracting the value for 0.25 from 0.75 and multiplying by 100 gives me the expected number of counts in the next bin, and so on, and so on. And here I have the numbers that are the bottom row of the middle of that same table. Then we define the usual sort of chi-square function, only this is the simplest one ever. We've got a vector of observed values, a vector of expected values, and we just sum up the square of the difference divided by the expected value. And from that, we can calculate the value of the chi-squared function and store it in the variable chi2, and the answer we get is 7.4. Now that on its own doesn't really mean very much. By the way, it's not the value given in the textbook, but the textbook is wrong. I'm correct. I discovered this finally when I tried to reconstruct this value by a permutation test and discovered that the third term in the calculation in the book is just plain wrong. So the question is, how probable is it to get this large a chi-squared value? If this is an improbably large chi-squared value, these data probably don't come from the exponential distribution. If numbers randomly generated from the exponential distribution frequently give a chi-squared value larger than this, then we certainly can't rule out the possibility. So we'll calculate the p-value. That's the function p chi-squared, the distribution function, with lower dot tail equals false, so we get the probability that chi2 exceeds the given value, and the comma 3 means 3 degrees of freedom, and when we calculate this we get 0.06. Hey, you say you've done something wrong. That's not what it says in the textbook. No, I'm right. The textbook is wrong. Another way of getting the sum of 100 numbers from an exponential distribution is to use a gamma distribution. And you saw in the very first script for this week that the gamma distribution leads rather nicely to a chi-squared distribution. But now let's take a resampling approach to this. Suppose we just almost 10,000 times, 9999 times, do a calculation where we generate 100 random samples from the exponential distribution with parameter 1, figure out how many of them give less than 0.25, etc., etc., and then calculate the chi-squared function evaluated on the actual number of counts that we get from this randomly generated sample and the expected number of counts, and plot a histogram of the result. There's the histogram, and what do you know? It agrees quite nicely with the density function for the chi-squared distribution, this time with 3 degrees of freedom because there are 4 entries in the table. On that, I can plot a vertical line for the value that we observed, and then, well, it's kind of ambiguous. About 6% of the time, the chi-squared that you get from a random sample exceeds the number that we saw. So, maybe this indicates that they weren't drawn from the distribution. Maybe it doesn't. You can't really say anything for sure. Now, in that case, the assumed distribution was totally specified, no free parameters. This next topic, which is much more interesting, is example 311. It's based on baseball. And we're going to read in a CSV file to create a data frame about the Philadelphia Phillies in the year 2009 with the outcome of every game. We're only interested in the column that specifies the number of home runs per game, so let's pull that out using the subset command, and let's calculate the mean number of home runs. Why are we going to do that? Because a plausible hypothesis for home runs is that they're Poisson distributed. That each time a player comes to bat, there's some probability of hitting a home run, and the number of home runs per game results from summing that up. Anyone who knows anything about baseball knows that just isn't true. There are some players that are much more likely to hit home runs than others, and more importantly, there are some pitchers that give up more home runs than others. So I would have guessed that a Poisson distribution would be a bad model for this. Shows what I know, as you will see. So let's make a table of the number of home runs. There it is, and you look at this. You don't do chi-squared when you have tiny counts. So we should really combine the 4 home run and 5 home run counts. Let's work with these 5 numbers. Now let's assume the data are Poisson. R has built in the density function for the Poisson distribution, and we will compute the probabilities for 0, 1, 2, and 3 home runs using a value of lambda that makes the expected number of home runs come out right. And you can check with the textbook. This is exactly what you get in table 3.10. And then, of course, you can compute the chi-squared function for the observed number of home runs and the expected number of home runs. And the value you get is 0.84. And you can ask, how probable is this? Well, you've got to use a chi-square distribution, and the number of degrees of freedom is a bit tricky here. The number of degrees of freedom is 3 because while there are 5 entries in the table, and any 4 of them determine the 5th, we estimated 1 parameter, and that cuts down the number of degrees of freedom by 1. So for the p-value, we use 3 degrees of freedom, and we get a number that coincidentally is almost exactly the same as the chi-squared value. It's 0.84. That means that 84% of the time, a distribution of home runs resulting from random selection from a Poisson distribution generates a higher chi-squared, a larger disagreement with the expected value than what we observed. So the Poisson model really seemed remarkably good. I was surprised at this. Now here's another way of doing this. We can say, let's simulate 10,000 seasons of baseball. Back in the early days of statistics, this would have been infeasible, but it's perfectly easy for us. So we use the rpos function with parameter lambda to generate for each season 162 random samples. and we then count up the number of times we get 0, 1, 2, 3, or more home runs. We compute the chi-squared statistic for this number of counts relative to the expected number of counts. We store those results, and then we show off a histogram of it. You compare this with the chi-squared distribution. Yeah, it's not a great distribution, not a great fit, but it's not bad. I think the explanation for this is that the expected number of home runs per game is on the small side, so you don't expect a chi-squared test to work particularly well. Here is the actual value of chi-squared, and it is clear that the probability of getting a larger chi-squared value is really quite large. So the Poisson model works pretty well. The p-value that I got out of this was 0.93, which is quite different from the result from the chi-squared test. And my own personal view is I trust this p-value more than I trust the one from the chi-squared test because the actual number of samples is rather small. Okay, that ends this script, and the one new piece of information I remind you is when you have to estimate a parameter from the data, you subtract 1 from the number of degrees of freedom.